Welcome to lecture 39. In this lecture, I will talk again about solving the U1 partition function, but I'll do this in a different gauge, the temporal axial gauge, or TAG for short. In lecture 35, we defined the partition function for a pure U1 gauge field as the path integral over the gauge field A and the ghosts C bar C of the exponential of minus the sum of all the individual parts of the action. Here, the gauge part was just the field strength tensor FAB squared. The gauge fixing part was the gauge fixing condition squared and the gauge fixing parameter psi, which is arbitrary. And the ghost action was the action that was giving us the determinant of the gauge fixing condition. The field strength tensor for a U1 gauge field is just dA AB minus the opposite combination, and G is an arbitrary gauge fixing condition that depends on A. We solved the path integral, this one here, for the class of covariant gauges in lecture 36, where the class of covariant gauges is the class of gauges where we took the Landau gauge condition for G of A. In this lecture, I want to repeat this calculation, but choosing a different gauge, the temporal axis gauge, where I set G of A is minus A of naught. The minus is just it's just a convention to make the writing easier. And it's called the temporal axial gauge because the zero component is the time-lag component of the gauge field. The reason for doing this calculation in a different gauge is that the math works out slightly different than in the covariant gauges, and it is sort of interesting to see what the differences are, in particular when trying to interpret the physical parts of the calculation. Okay, so let's do this. In the temporal axial gauge, the ghost action can be written in this form because we have the derivative of the gauge function with respect to the gauge fixing parameter. The gauge is A naught, so A naught under gauge transformation goes to A naught minus D0 alpha, and the derivative of D0 alpha with respect to alpha is just the D0, so that gives rise to the D0 in the ghost action. The ghost action again does not depend on the gauge field, so that means that the partition function again separates into a part that just depends on the gauge field, which I call CA, and a part that just depends on the ghost fields, which I call Z ghost, where Z ghost is the path integral over the ghosts C bar C of e to minus the ghost action. The gauge field part contains all the parts that were given in the previous slide, namely the gauge field part FAB squared, and the gauge fixing part, which in temporal axial gauge is just A naught squared. Since the path integral for the gauge fields is quadratic, we can perform the path integral for arbitrary gauge fixing parameter psi. This is possible, but it's sort of also possible for us to just ignore using psi as a check. So we can make our life considerably easier if we pick a particular value for psi. And the value that I want to pick now is that I want to send psi to 0. The reason for doing this is that if I send psi to 0, the gauge fixing condition, the exponential of minus 1 over 2 psi integral over A naught squared, just becomes a representation of the delta function. Particularly if I write the exponential of the integral over x, I can think of the integral as a sum. So an exponential of the sum is the same as the product of the exponential. And then the product of x then represents this product of all space-time values. And then e to the minus A naught squared over 2 psi with the limit psi to 0 is a representation of the delta function. So I get the delta function of A naught at every point in space-time. So clearly this is a big simplification because we can use this to do the path integral. Let us see what the individual pieces are once we sort of do or aim for doing this integration over A naught with the delta function. we have that the field strength tensor FAB separates into component F0i, F0i, and the spatial components Fij, Fij, we have not restricted the sums I and j, so that means that I still have to account for the factor 1/2 that we have on the left-hand side. We can write this out in components. The Fij is still here, and F0i becomes d0ai squared minus 2 di a naught d0ai plus di a naught squared. When we then integrate over a naught with the delta function, that restricts all a naughts to be 0. So this term vanishes, and we are only left with these two terms in the action. And that gives us the following result for the partition function ZA. As a reminder that we only now integrate over the gauge field parts that are spatial, I've indicated as an AI in the integration measure, because we already integrated over the A naught part. As in lecture 36, we then go ahead by Fourier transforming the spatial parts of the gauge fields into Euclidean form momenta K. The K here still is the full 4-dimensional Euclidean wave vector, so it contains the Matsubara frequencies, even though we only have the spatial parts of the gauge fields. We have the spatial parts of the gauge fields, but they carry full space-time dependence. If we plug in this Fourier transform, we find that the partition function now is sort of in the form that we can clearly see the form of the operator in Fourier space. So we can integrate that. And one might wonder whether we still have a problem similar to the problem we had in lecture 35, where this essentially created a divergence. So let's inspect that now. So in lecture 35, we had a similar expression. We were integrating over all gauge field components, and we had an operator here, which is k squared delta AB minus ka kb. That was a problem because this matrix that we have in here has a 0 eigenvalue. You can check that by figuring out that if I take the matrix and I contract it with vector ka, that gives 0. So ka is an eigenvector of this matrix with 0 eigenvalue. If you have a 0 eigenvalue, then the determinant of this matrix is 0. So the inverse determinant is not well defined. So that was the original problem that we had, for which we invented the gauge fixing. Now let's inspect our result for the result that we had on the previous slide, equation 39.11. The corresponding determinant that we have in the expression for ZA is k squared, capital K squared delta ij minus ki kj, where I here are the spatial parts of the 4 vector, and k squared is the Euclidean form momentum. So it contains the spatial as well as the time lag parts. So the question that sort of comes to mind is whether this expression has a similar problem than the expression we had in lecture 35, and whether the temporal axial gauge, if I send psi to 0, is not a valid or useful way to get to a result. To study this, we can decompose the matrix we have at hand by introducing 2 projectors. Let me call them Tij for the transverse projector and Lij for the longitudinal projector. There should not be any square here. The square should be in the denominator. So the transverse projector is called transverse because it is vanishing when I contract it with the spatial ki. And the longitudinal projector is longitudinal because it gives back the same projector if I contract it with the spatial ki. So in that respect, they are longitudinal with respect to spatial momentum k. In terms of these 2 projectors, we can decompose the matrix that we have by writing its capital K squared Tij plus omega n squared Lij. And we see by looking at this expression here that unlike the problem we had in lecture 35, this expression here does not have any zero eigenvalues. It would have zero eigenvalue if, for instance, this term was not there, but it is. And the reason is simply that this matrix has a form where we have the Euclidean form momentum squared here in front of the delta function. And that's why it's not only proportional to the transverse projector. So that's why it doesn't have a zero eigenvalue. We can look at the multiplicity of the eigenvalues by looking at the traces of the projectors. The trace of the transverse projector is 2. The trace of the longitudinal projector is 1. So that means that we have, backing up, we have eigenvalue k squared with multiplicity 2 and eigenvalue omega n squared with multiplicity 1. So we find that the determinant for the ZA in temporal axial gauge is given as the following expression. It's the exponential of -1/2 sum over all Euclidean form momentous logarithm of k squared squared, because the eigenvalue was k squared. It comes with multiplicity 2. -1/2 sum over all Euclidean momentum k logarithm of omega n squared, because the eigenvalue for the longitudinal projector was omega n squared, and it comes with multiplicity 1. The ghost contribution was just the ghost integral with the single temporal derivative. So that just gives e to the plus sum over k logarithm of omega n. If we recall that the total partition function is just the product of these two, we find that the ghost part again cancels part of the gauge field part. You can see that because we can for instance, write this expression as 1/2 logarithm of omega n squared, then it cancels precisely the logarithm of omega n squared in the gauge field part. And we find that the total partition function in temporal axial gauge is just e to the -1/2 sum over k logarithm of k squared squared. Just a little remark, that cancellation was purely in the longitudinal sector because the eigenvalue omega n squared that was cancelled by the ghosts was the one that came from Lij, which we interpreted as the longitudinal projector. So we find that the end result in temporal axial gauge matches the result for the partition function found in covariant gauges in lecture 36. And we find that since the longitudinal part cancels, only the transverse photon contribution contributes to the partition function. That's what we expect from physical reasoning anyways, because we have an electromagnetic field and only the transverse parts should be the physical ones. And here in temporal axial gauge, that's actually the way that it works out in the calculation. The cancellations between photons and ghosts work differently in the different gauges that you can see directly by comparing what I said now with what I said in lecture 36. But the end result is the same as it should be, of course. And this concludes the present lecture.